In this video, I'm going to demonstrate how to write precipitation reactions. And a precipitation reaction is just a reaction where the chemicals in a solution react to form a solid or a precipitate. And the example that I'll be using is when an aqueous solution of sodium chloride is mixed with an aqueous solution of silver nitrate. So there's just a little bit of nomenclature that you need to understand. This AQ subscript, this stands for aqueous. And aqueous just means that the ionic species is dissolved in water. So if you look at this cartoon image of an aqueous solution of sodium chloride, that means that the sodium chloride is completely broken up into its cation and anion pairs. And all of the cations and anions are completely surrounded by water. And if you're wondering what an aqueous solution of sodium chloride looks like, well, it just looks identical to pure water. So if an aqueous solution of sodium chloride is mixed with an aqueous solution of silver nitrate, which also looks like this, what we will form is a liquid with a crystalline precipitate, crystalline white precipitate, and that precipitate is silver chloride. So if you look here, in the cartoon, I've denoted silver chloride with the subscript S. S means solid, which also means a precipitate. That forms because the silver cation interacts with the chloride anion strongly enough to form a solid. Now, what you also see is that you also have sodium cations and nitrate anions still present in solution, which you can't see. This white solid is the silver chloride. You can't see the sodium or the nitrate because they're still dissolved in water. They do not interact strongly enough to form a precipitate, so they are just left in solution. And what you'll hear later is that these are called spectator ions because nothing happens to them. There's no change. So the first steps in writing the precipitation reactions to explain what happened here is to first you have to identify the cations and anions from the starting salt solutions, which are our aqueous solution of sodium chloride and silver nitrate. So in order to do that, we would just take our sodium chloride and we would say sodium chloride can break up into a sodium cation plus a chloride anion, and silver nitrate would break up into a silver cation and a nitrate anion. So how did I know that sodium formed a +1 cation and chlorine formed a -1 anion? Well, in this case, I would just simply go to the periodic table. And if you look here, column 1, everything in column 1, all these metals form a +1 cations, and everything in column 2 form +2 cations. +1, +2. And anything in column 7 here, those all form -1 anions. So in the case of sodium chloride, it's really very simple. Sodium forms a +1 cation, chlorine forms a -1 anion. Silver, which is also a metal, it will also form a cation, but we don't necessarily know the charge of the cation from the periodic table. So in this case, we would go and we have to remember what our polyatomic ion charges are. So let's make this a little bit bigger. So anytime you see, say, an N, P, or S followed by a bunch of oxygens, you know that you're going to have a polyatomic ion or an ion made up of many atoms, poly meaning many. So here you can see the nitrate group. This has a -1 charge. And the polyatomic ions are something you just have to memorize and memorize the charge of. So since the nitrate has a -1 charge, in this case we have one nitrate group with one silver group, we know that the silver has to have a +1 charge so that the two charges neutralize each other. So now we want to identify the new cation and anion pairs that could form. So we would combine the silver with the chloride, and we'll combine the sodium with the nitrate, and what we will get is silver chloride, sodium nitrate. And what we now have to do is we'll identify, based on our solubility rules, if there are any precipitates. So we want to decide, are these species, these new species that form, going to be aqueous, or will they be solids or form precipitates? So at this point, we'll have to reference some type of solubility table. So if we take a look at the one that I have here. Okay, so what you can see is that we have at the top compounds that are generally soluble or generally dissolve in water. At the bottom are compounds that generally form precipitates or do not dissolve in water. And so with our sodium nitrate group, we can look and we say, okay, nitrates are generally soluble and there are no exceptions. So in that case, this sodium nitrate is going to form an aqueous species. It's going to stay dissolved in water. So we put the AQ subscript. Now, silver chloride, let's see, things that contain chlorine are generally soluble except for chlorides with chlorine combined with silver compounds such as AgCl. These are exceptions, so those form insoluble products. And so we would put an S subscript, meaning we have a solid or we have a precipitate. So now we've completed the second step, which is determine if there are any precipitates. And now we're ready to move on to the third step of writing the balanced molecular equation. So the balanced molecular equation just involves writing down our initial species, which are an aqueous solution of sodium chloride and silver nitrate, with our subscripts AQ, meaning they're aqueous, and they went to form an aqueous solution now of sodium nitrate plus the solid precipitate silver chloride. And you want to make sure that your equation is balanced at this point, which ours is, because we have one sodium on each side, one nitrate group on each side, a chlorine group on each side, and a silver group on each side. But your equation would not necessarily be balanced, so you have to make sure it is balanced before you proceed to the next step. So the balanced molecular equation is one way of representing a precipitation reaction, but there's another way called a total ionic equation, and that does a better job of representing exactly what does happen to the individual ions in the solution. So in the total ionic equation, you break the aqueous species up into their cation and anion pairs, since that is how they actually are present in the solution. And I'm adding all of the AQ subscripts to denote that they are aqueous species. So on the right side, the sodium nitrate is also an aqueous species, so that has to be broken up into its cation and anion pairs. But the silver chloride is our precipitate, so we leave it associated with this S subscript. So if you go back to our cartoon image here, you see that the total ionic equation really represents what really happened, since the sodium and chloride is broken up into its cation and anion pairs, as is the silver nitrate. And then when we form the solid precipitate, the AgCl solid, you also have the sodium and the nitrate left floating around in solution. And so while the total ionic equation does represent exactly what did happen in our precipitation reaction, you'll see that you have some things that are the same on the left and the right side of the equation here. And let's see, so the sodium is the same, the nitrate group is the same. And so these are called spectator ions. So they're just spectators. They're just watching what's going on. They're not really participating in the precipitation reaction. So if you just want a neat and clean version of exactly what happened, we can remove the spectator ions and write what is called our net ionic equation, which just shows our precipitate forming from the two ions that interacted to form the precipitate. So that's all there is to it. So hopefully now you're ready to try writing your own balanced molecular equations, total ionic equations, and net ionic equations.